Welcome everybody to today's webinar. Today's topic is going to be cloud computing with HELYX and Penguin Computing on Demand. My name is Dan Combest. I'm manager of ENGYS LLC here in the US. I'm joined today with Will Cote. He's the director of cloud services for Penguin Computing. And some of the topics that we'll cover today and some of the goals. First off, I'd like to introduce ENGYS and our CAE software innovations and provide an introduction to Pod to get up and running quickly and show how to run HELYX directly within a web browser using a cloud workstation provided by Penguin Computing. And then finally, just give a little glimpse of how to submit jobs to Pod directly from within the GUI. Now, we'll save all of our questions to the very end, and we can continue the conversation via email post-webinar. In fact, if you have a question, you can just reply to the webinar invite and those questions will go directly to me. And I'll make sure to either answer them or pass them on to Will and see if he can answer them as well. Just a little bit about ENGYS. We are global providers of CFD products and services. And we were founded in the UK in 2009. So we just finished celebrating our 10th year of business. And we've always been focused on enabling open source software in industry. We've had a lot of experience with foam and OpenFOAM. So if you're familiar with OpenFOAM, you know that it came out as OpenFOAM around 2005, 2006. And before that, it was a closed source proprietary code called Foam. So we have developers within ENGYS who've had experience with it since its Imperial College days. We have 7 offices worldwide, 1 in the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. We also have an established distributor network around the world in Japan, South Korea, here in the US, France, and also in Spain. Just some information about some of our products. Our kind of flagship product is HELYX, which is a general purpose open source CFD software suite. This includes a mesher, solvers, different applications. There's post-processing, so it's more of a general purpose CFD tool. Then we have Elements. Elements is specifically aimed towards the automotive industry. So it's a superset of HELYX in that it also has the capability to build in best practices for external aero simulation of vehicles. So it dramatically speeds up setting up these cases compared to HELYX and even other CFD software. Then we have HELYX add-ons, and within add-ons, these are additional capabilities like continuous adjoint optimization, block-coupled solvers, solvers specific to marine hydrodynamic simulation, and then also advanced multi-phase modeling. And then finally, we have HELYX OS, which is a free GUI to drive standard OpenFOAM. You can go to our website, engys.com, and you can search around and find a link for HELYX OS to download that. Just some upcoming events. The OpenFOAM workshop is this summer, and it has switched to a virtual event. So you can find more of that information on engys.com/events. You'll see a link to the 15th OpenFOAM workshop. ENGYS is still the official sponsor of OpenFOAM Workshop 15, so it should be a really great event. Now it can reach more people around the world, so there still should be a lot of great presentations there. In the spirit of more virtual events, we actually have 2 upcoming webinars. The first webinar in April is about enhanced topology optimization with multi-objective continuous adjoint. So I'll be leading that one. And then the next one is surface optimization with continuous adjoint. So April is all about adjoint with our webinars. And then also, if you like to read about engineering content on the web, you can go to blog.engys.com and look at our blog. You'll find information about research and development at ENGYS, past webinars, continuous adjoint, HELYX, and elements related material. All right, so to start out the webinar, I'd like to give a little bit of a motivation of why we're working with Pod, and then I'll pass off to Will, and he'll talk about Penguin Computing and Pod and do a walkthrough, and then I'll take it back and talk about HELYX, and we'll end with some take-home messages. So first off, what's the motivation for HELYX on Pod? I wanted this to be more of why our customers like to use Pod. And first off, clients needed an easy option for scalable HPC resources. Now, there's many different reasons why I would categorize this as easy. We'll see, being able to use a workstation through the browser, that's something that's really important. So somebody is able to continue working exactly how they would have back in their office. And we also wanted to enable bare metal resources for customers as opposed to virtualized. And the reason why we wanted bare metal is because it'll scale better. We can work with larger simulations. So specifically for the automotive industry, you'll need to go to instances of much larger than 96 cores or just a few nodes. You may need to go up to hundreds or more than 1,000 cores and be able to run very large simulations. And then also we wanted a capability to for customers to trial HELYX and Elements and try this out very easily. Why choose HELYX? Well, first off, it enables meshing, setup, solving, and post-processing in a single software. If you're used to other open source tools, you have to physically build your tool chain. What software am I going to be using to create my mesh? How am I going to set up all of my cases? What scripts do I need to write? Then solving which solver do I need to use? And then which post-processing tool am I going to use? Am I going to use ParaView, or am I going to use TechPlot or EnSite or some other tool? And just also is experienced with support, and we have detailed documentation. Like I mentioned before, we've been working with foam for a long time. I started working with OpenFOAM in 2006 before I did my graduate work, so I personally have had a lot of time with the code and with Elements. And then also the features within HELYX, they rival other commercial codes, so it's actually very easy for customers to move over from other commercial codes and get the same features, the same capability at a more preferred price point. Okay, so at this point, let me exit out of this and then let me pass over to Will. Perfect, we can see your slides now.
Great. Well, good morning, everyone, or whatever time of day it is. Hope everyone's doing well today. I'm going to keep my demonstration of Pod as short as I can because I think Dan's got some really interesting things to show us, and I'm pretty excited to see them. But I did want to tell you a little bit about Pod, or Penguin Computing on Demand, and about Penguin Computing in general. We've been doing HPC and data center Linux solutions for well over 20 years now. And we've been doing what we call Penguin Computing on Demand for nearly 10 years now. And that really gives people access to true HPC clusters from anywhere in the world, just from your desktop. We build a lot of very large systems. We've got 10 of them on the top 500 list right now. We've got installations all around the world. And we've been supporting that with our own software stack for 17, 18 years now. We've got some US offices. We're sort of spread out. While that just shows California, Oregon, and Georgia, a lot of us are remote. We're a very flexible company in that way. And then we've got offices in UK and Japan also. So pod is, in its heart, a real HPC system, a traditional HPC system. We don't use any virtual CPUs, so no hyper-threading. You're always the only one on any particular node. Even if you're not using the whole node, you're never going to be sharing a piece of hardware, compute hardware, with someone else. We've got low latency, high speed interconnects, either InfiniBand or OmniPath, depending upon what systems you're using. And it's all non-blocking because we're never sure what people are going to be doing. We also have a great HPC support staff. This is what our customers always tell us when we ask them why they continue to use pod year after year, is they feel like they really get the sort of support they need. We don't just throw out hardware and say, go for it. We actually have people that will help you in your workflows and help you get your work done and not just make sure the system's running. In addition to the fine products from ENGYS, we have hundreds of others that are pre-configured and ready to run, either commercial or open source. And we do have the remote desktops for 3D post-processing. I really like those. You'll get to take a look at those pretty soon. And we also try to make sure that our pricing is really predictable and really transparent to all our customers. The complaint we hear about cloud all the time is people get bills and they really can't explain why their bills got so high. But we want to make sure that you can keep track of what you're spending and control your spend on pod. In that, you can see it's a clear and predictable billing. You pay by use. There's no commitment. There's no sign-up fees. You get charged by the core hour that you use. Meter that to 3 seconds. We never round up or anything. You pay by the average amount of storage you use per month. We don't charge for uploading or downloading any of your data or results. You will get a private login node for free that you can use to transfer files back and forth. That doesn't include the Scyld Cloud Workstation that we'll be seeing a little bit. That's actually got a GPU behind it, and it's quite a bit more expensive for us to maintain. So there's a charge associated with that. You can also download, you'll see, I'll show you some online reports that you can look at. But you can also download your accounting and reporting in Excel format, so you can, easily account for different projects and things like that. There's many ways to work with pod, and I'll show you the web portal real quickly here. And that's for account management mostly and your usage reporting. In this audience, there's also the option of submitting jobs through a GUI. This audience would probably not use that feature. We've got the remote desktops that Dan mentioned earlier, and you can also SSH to your login node if you want to submit jobs traditionally. So that's all for slideware. Let's take a look at what pod looks like. So this is pod portal. I logged in just before we got on here. And you can see this is an overview of my account. So far this month, I've run 9 jobs. That's actually since midnight last night because our billing day stopped yesterday. And I can see what I've gotten in 2 different locations. We've got 2 main locations for pod, MT1 and MT2. Everyone will probably be running on MT2. Those are our newest, fastest nodes. And I can see what other users I've let use my account. I can manage those users if I'm the account owner. So I don't have to make any requests or anything to manage users. I can actually add users, take users off, give them different capabilities. We're going to skip the SSH keys here. That's just something if you're going to log into the command line. We only allow public-private key pairs. So that's a way to upload your private key. Let me go back a month here because nothing's obviously has happened today too much. And I can see what I did last month, how much storage I used. I can turn the storage off. I can look at the jobs I've run, core hours I've used, how many hours I've had chargeable VMs up, that sort of thing. I can see which users actually generated all that work. And I can see what jobs, what projects those jobs were assigned to. So you can assign jobs to projects and then keep track of it like that. And I can also see what my login node detail is. I use obviously quite a few VMs last month, chargeable VMs. I can download a custom Excel spreadsheet or just hit the button to get one for a month. You can also manage your usage. So you can set up usage alerts so that if you or one of your users hits or comes close to a threshold, you'll get an email alert that tells you that you have gotten close to that threshold. You can optionally have your users notified, and you can also do it by group if you want to. We'll take a look at the resources I've got in use on MT2, which again is our newer data center. I can see I've got a login node that I've called GPU01, and it's a type of SCW or Scyld Cloud Workstation. I've also got a free node there, and I've got a fairly hefty VM there that I might use for compilation or actually for Scyld Cloud Workstation if I'm not doing 3D work. That works quite well for a 2D desktop. It's very easy to get to your workstation. Just click that and log in. Well, Dan's going to show you some of their software. I just wanted to let you know there's other things you can use too. There's ParaView, for instance. You could use ParaView for your visualizations. I'm actually about 1,500 miles away from the workstation I'm working at right now. And to me, it looks very, very much like it's on my local desktop. And again, you might decide you want to do some other work. Maybe you want to do some amateur weather forecasting, use our cluster to do that. Or maybe you want to use some CAD tools. That's all available on Pod. The other thing you might want to do is share your screen with someone else. I can invite guests to share my screen, up to 10, I believe it is now, simultaneously. And we can work collaboratively because we can pass the keyboard and mouse around amongst us. I'm just going to sign out of this now. And I'm going to give the presentation back to Dan because he's going to show us a lot more interesting stuff than this. Thank you very much.
Thanks a lot, Will. That was great. Let's see. Let me make sure people can see. All right. Can go ahead and see mine. So today I'll walk you through using HELYX on the Cloud Workstation through the browser. Will did a great job at introducing a platform that's kind of everything you need to do before, or you can do before you get to this point. So once we've started up the Cloud Workstation, then HELYX users will have this shortcut on their desktop. And when you start HELYX, or if you start Elements, you'll always be met with this HELYX launcher or Elements launcher. And so here's where we set up things like client-server connections. And client-server connections are a way for us to connect from the GUI to different computational resources. So for example, I've got 3 right here. So the first one that I'm looking at is localhost. This will use the workstation that I've been given, and so it should be 12 cores, and it has a pretty significant amount of RAM. It has a GPU. Now these other client-server connections that I've got right here, these are actually pointing towards pods different queues. And so they'll have different core counts per node. And so if I was doing a much larger job, I would simply click on this, work through the GUI, set up my mesh, set up the case, and when I submit or submit a job to mesh, it will actually submit directly to those queues, which is very nice. And it selects how many nodes that we need to pick, so you don't need to go down to that fine-grained level and select how many nodes. So this kind of setup right here, these two run modes, as we call them, these are things that can be provided by ENGYS support to users on pod. So today, let me just work with localhost. And I'm only doing this today because this is a smaller case. We can move through a little bit faster. But in essence, I could set up a case, and once I'm happy with that, then I could go back and change my run mode. I could increase my mesh density, and I could submit it to hundreds of cores very easily just by changing my run mode. All right, so let me start off and create a new case, and let's set up something on the desktop. So let's just do radiator, and then let's just do 8 cores. Whoops, let me choose a different name, radiator V2. And before I go any further, let me get rid of this control. Whoops, bring it back. Let me actually go full screen. All right, perfect. So now I've got my new case. Let me just maximize this. Now the overall workflow of HELYX is that we work through these different tabs, and within the tabs, we move our way down these different tree entries. So we start with the mesh tab, then we'll go to setup, then we'll go to solver, and then we can go to view and perform some post-processing tasks. So let me start with the mesh tab, and HELYX comes with a cut cell meshing approach. This is something that you'll see with ANSYS and StarCCM. They both use cut cell meshing approaches. This is something that ENGYS has developed throughout our years of operation. We have one central developer for our mesher, Andrew Jackson. So he spends quite a bit of time improving the mesher on a daily basis. So let me start at the top and choose my meshing algorithm. I can choose the default layer addition algorithm or something that's called the dualized layer addition algorithm. The benefit of the dualized is that we're ensured 100% layer coverage. So this works perfectly for steady state cases and different RANs, turbulence approaches. So dualized is something that I usually select for steady state. Base mesh, this is something, since we're using a cut cell approach, you have to generate a background mesh, and then from that background mesh, you cut out your STL geometries. It'll refine where the geometry intersects the background mesh, then we'll add layers, and then we'll sweep away cells that we don't need, and then snap these cells to the surface of the STL and regain our original geometry. And I'll show you exactly what that means. All right, so let me start by just choosing a background mesh and use the default. Let me import my geometry. So I can import different types of geometry. You can see down here at the bottom, I've got STL, OBJ, IGES, and STEP. And what happens is if we import IGES and STEP, it'll take those CAD files and it will triangulate those surfaces and generate faceted surfaces. So if you have a high quality STL generator anyway, it's better just to go ahead and use that. Next, we can select if the geometry is in millimeters. If we don't select this and then we find out that the link scale is wrong, we can just right click on the geometry and actually change that. I know this is in millimeters, so we're automatically going to scale things. Let's just hit open. So here we've got a simple radiator. It's all one STL. However, what we'd like to do is we'd like to take this STL and we want to break it up into different STLs. That way we can apply different boundary conditions to them. Now I could have done this in my CAD software ahead of time, but it's always very handy to be able to do this from within the GUI instead of sending an email back to the CAD engineer or having to check out a license of your CAD software. So we're able to go through and select different surfaces that we want to become these different boundary conditions down the road. So let me just go through quickly and just select off a few of these just to show you how we can select things and split them off. Also, one of the main benefits of being able to split off different surfaces is we may need to change the different types of or cell size or layer addition, how many layers are being added inside of these fins compared to the rest of the geometry. Let's just do inlet fins, and then let me do outlet fins. There's multiple different selection criteria. Here I'm using something called feature angle, so it looks at the feature angle of the normals of the different triangles that make up the STL, and if it sees an angle difference between the neighboring triangles, then it will select that based on this angle right here of 30. Let me go through and just select a few more. All right, last one, gotcha. All right. Now I could go into much more detail and I could select out different patches if I want, but for today, I'm just going to select my inlet, outlet, my inlet fins and outlet fins for the flow that's going to come in this tank right here, flow through these fins, and then move around through this tank and through the outlet fins over to the outlet region. And so for today's analysis, maybe I want to assess the pressure drop from the inlet to the outlet. And then also I might want to see exactly the flow pattern that's occurring within the system. So for inlets, let's set everything to a 3-3. And so because this is a cut cell meshing approach, what it does is all of our local length scales are in relation to the background mesh itself. So what does it mean when I say a 3-3? It means it takes the base mesh spacing, which is 1 centimeter, and the local cell spacing is going to be 1 centimeter divided by 2 raised to the 3rd power, which is 1 millimeter. And for these inlet fins, let's just say that I want to add 3 layers, and also for the outlet fins, let's just add 3 layers. Perfect. Let's not add any layers into the radiator tanks. If I wanted to, I could add them. I think in the final result that I've got here, it's actually has layers in there as well. The last thing that I need to do is just select a material point. And so if I know that material point, I can just punch that in. Otherwise, I can use this light bulb exactly how I did, and I can just move it around and make sure that that's in the volume where the physics, where the simulation is going to take place. I could also use this button right here, and this will take it to the center of the bounding box, but I know that because I'm missing something in the middle here, it's going to need to be placed manually. All right, perfect. At this point, I could create a mesh. That actually will take a few minutes, but I'd like to go ahead and just set up the boundary conditions. So what I can do is do something called virtualization. Virtualization will take all of the surfaces, take all of the cell zones that may be porous media, and it converts those to these virtualized patches. The reason why we like to do that is because now we can go into the setup component and we can actually set these as boundary conditions. We can set the physics. So for this case, I'm going to do segregated, steady, incompressible. If I had access to the adjoint add-on module, say I wanted to optimize the shape of this tank right here or reduce swirl in this region, I could select adjoint and I could go through and set up that problem. Materials, let's change this to water. Of course, we can put in a new fluid, and that could be some sort of coolant. For modeling, we're going to choose Reynolds average Navier-Stokes, so RANS, and then we can select from different models. I'm just going to leave the default of K omega SST. Now we need to go through and set up the boundary conditions. For the inlet, let's set it to type inlet. I'll use a type flow rate. And because this is a small device, I'm going to lower that flow rate. Inlet fins, by default, that's a wall outlet. Let me set that to type outlet. Outlet fins, those are walls as well, so it's a no-slip boundary condition. And then the radiator tanks themselves, those are also walls and no-slip. There's no cell zones. If there's porous media, then we could set up the porous media in cylindrical coordinates or regular Cartesian coordinates. If we wanted to, we could also set up different thermal sources if we're working with a thermal simulation. So there's lots of different source terms that we can add to the different transport equations, MRF, things like that. Next, I've got numerical schemes. Here we have control over the gradient terms. We've also got control over the advection terms. Let's just choose bounded upwind first order for this case. I always like to use first order starting off and make sure that I have all my settings correct. Solver settings, these are the inner iteration residuals, so how deep at each time step of our simulation, how deep are we going to go with the residuals? Also relaxation factors. If we want, we can use a velocity limiter. If we're expecting spikes in the velocity in the very beginning as we're trying to converge, we can select that. Runtime controls. Start time, end time. For this case, we only really need 500 iterations. How often do we write? Let's write just at the very end. What is this write format? If we want to be able to read the text files by loading them into a text editor, we can use ASCII. Otherwise, we can use binary to save some space in our directory. So I'll just use ASCII for now because I'm not going to run this. Write data. So here we could output some VTK slices. We can output insight data if you have access to insight. So if you're running really large cases, automotive cases, and you want to write out insight gold format data, this is the place where we would set up insight gold format. This could also be set up very similarly in elements. Next, we've got field manipulation. Field manipulation is a way to perform in situ analysis or in situ derived data generation. And what I mean by that is we have our principal variables of velocity, pressure, and then we also have K and omega in this case. But what if we want to calculate Y plus during the simulation? What if we want to calculate vorticity or total pressure coefficient or wall shear stress or some other derived component? And then also we can do things like field averaging. So if we're doing a transient simulation and we want to capture the average velocity over that simulation duration, we can do that. Let me just select field process. And let me add, so we've got lots of different types. There's these generic operations on different variables. And then we've actually got more specific. So if we're doing a thermal simulation, we can look at convective wall heat transfer coefficient. We can look at near wall velocities. We can look at skin friction factor. Here, let me just select Y plus. That's something very familiar. This will be calculated at every write time and it will be outputted at every output time. So because I've set this to 500, Y plus is only going to be calculated at the very end of the simulation. That's fine by me because that's really the only important data point that I need. Monitoring functions. This is where we can monitor the simulation health. So what are the forces on this patch? If we're doing something with rotating turbo machinery, we can look at that and see exactly what kind of efficiency we're getting on a fan. I like to use monitoring functions to do things like volume reports. So a volume report will give me the min, the max, and the mean of these selected variables within the volume, okay? If I have a cell zone and I want to monitor the maximum pressure or the maximum velocity inside of a cell zone, I can just select a specific cell zone as well. Another really interesting one that I like to use, we can look at noise propagation, we can look at pump performance. I mentioned that. Zone forces would give us the pressure drop and the mass flux through porous media or any other zone. Let me do a surface report because I'm more interested in looking at the area weighted pressure average. So I could do flux weighted or area weighted, but for pressure, I'm doing area weighted. And I want to look at the area weighted average of pressure at the inlet. I know what the pressure is at the outlet because it's an outlet boundary condition and it's set to 0. And so I need to know the pressure at the inlet. So right now I know that. Next, I'll go to field initialization and I'll choose potential flow for pressure and velocity, and then I'll choose something called Prandtl initialization. This is based on a Prandtl mixing length approximation, and we'll use that to estimate K and omega. It uses the velocity field to estimate K and omega in this case. All right, at this point, I could hit this button that says run all, and what run all will do is it will mesh, it will initialize, and then it will solve the case. Now, in order to save a little bit of time during this demonstration, let me go ahead and just open up something that's already been run. Let's go ahead and do final. All right, great. So I've already got a simulation run. Let me go all the way to the View tab. Let me disable velocity really quick. Now, during the simulation, it will output the residuals. We'll see the inlet pressure. So here we've got pressure. You can see that with this plot, we've got this band. So this dark red line right here is the mean pressure at the inlet, and then this band right here is the min and the max of the pressure on the faces right there. So we have this idea of what the pressure values are over this patch. And homogeneity tells us how uniform that mean value of pressure is over that inlet patch. Perfect. Volume report tells us the min, the max, and the mean in the simulation. The reason why I like this is because it's a great indicator of simulation health. I say simulation health because in this case, if I saw a velocity of 10,000 meters per second, then I would know that probably something's wrong with the boundary condition, or something is wrong with the scale of my simulation, or maybe I have some problem with a mesh. So it's a great indicator of, hey, I need to go back and just make sure all my assumptions are correct and I've set up things correctly. Right, so in this case, we've got a velocity, average velocity in this domain around 0.25. If we want to look at something a little bit more detailed, all right, so it's around 0.27. You can see these tiny numbers in the left of these crosshairs. And then the band of the velocities go between 0 and 2.7 meters per second. Great, that's expected. Now I could go on and I could load the result in ParaView. If I had field view, I could load this in field view and also in Insight. But let's go on to the View tab. Here we can do several different things. So we've got these different objects where we can slice, clip, add streamlines. We can look at isosurfaces or look at glyph vectors. We can also do something called groups. So groups are, we can group together different objects. And so here, if I wanted to call this radiator shell, and the reason why we might want to create groups is because then we can adjust the, we can adjust the transparency of these different objects. We can put different data on different groups. So we can have one group that is half the geometry that has pressure. We can have another group that has the near wall velocity. We can use cuts on these groups and we can segment them out and separate them and generate really nice looking visuals in order to showcase our data and explain a concept more easily. All right, so once we click, if we click in a certain region, things that are lit up in green can all be grouped together. You'll notice right here that if I choose the volume mesh itself, only the patches will be something that I can group together. I can't actually group the STL surfaces together. So for this case, let me just do the STL surfaces, click OK. And then I could adjust the transparency of that, and you'll notice that I still have my patches right here. So let me adjust the transparency of my group itself. So let's choose pressure, and then let's load up the final time step just so that we have some colorful data. Okay. And then here we can check the back-facing style. So if you've got several patches that are overlapping each other, sometimes you'll see a little bit of a checkerboarding. That's just a visualization effect. And this is something that is present within VTK. We can change the back-facing style. Okay, great. So that's groups. And then objects, as I mentioned before, I've got slice, clips, streamlines, isosurfaces. Here, let's just look at streamlines. And let me load something that I've already done. And then let me load a group that I've already got that I had before. So you can barely see the group. The transparency is set very low. Bring that up just a little bit. Okay, so aside from groups, aside from these different objects, we can color the different streamlines. We can control exactly how these streamlines are injected into the system. Here I've got a point source. The point source is right here. I could also do by patch. I could use a line source. I can control things like the number of points and the streamline radii in order to create a more appealing visual. I can change what my color by field is. So let's change it to pressure. So here we've got pressure. Now, once I've got something that looks very nice, I can also do something called creating a scene. So these scenes are made up of different items. So here I've got the radiator group and then streamlines, and I can adjust a camera angle. I can adjust the background color. I can adjust what the user sees and the actual angle of the focal point and what the camera direction is. The reason why I like to do this is because if I've got several different cases that I'm running and I'm using this as like a base case, it ensures that when I save this to an image, I'll have the same image each time, which is very handy when you're trying to put this information into PowerPoint or some other presentation software or in a scientific paper or in a report. So it's very helpful. All right, I'll stop here. And there's many different features that I haven't talked about. One of my favorite is the journaling feature, where I could have recorded everything I did and it would have output that into Python, and then I could have driven all of these workflows automatically with Python. I did a webinar on that a few weeks ago. So let me jump back to my slides. And we'll finish up. So some of the take-home messages, I would say that, overall the benefits of Pod, using Pod fits how users currently work. There's a desktop that's provided. It allows more freedom of workflow. So I talked about using Python. If you're used to writing your own scripts, it's really very handy for that because it's very close to the HPC. So it's very easy. I can submit a job directly from that cloud workstation. And I can connect and submit to HPC very easily from within HELYX. I showed that I could just switch over to a different run mode and submit directly to different queues. And additional software can be installed. We'll mention that. They've got lots of different software there. One of my favorites, though, is the HPC support. I think the support engineer that I'm dealing with is probably listening now, but he does a great job. So I really like the support that I've received so far. And also HELYX on pod, this is just a rehash. We can mesh, setup, solve, and post-process. If you like to use pair view, you can also use that. We can easily expand HPC capability on pod. There's the functionality is comparable to other commercial codes at a lower price point, and it enables users to trial our software in an HPC environment. So in terms of next steps, if you'd like to trial HELYX and Elements on pod, reach out to ENGYS. Let's discuss your CFD workflow, your CFD problem. Let's set a design problem. Let's talk about what kind of physics you're using, what kind of boundary conditions, and that's best explained in like a PowerPoint presentation. Then we can set up a trial on POD or on pod. You can send an email to info@engys.com, or if you're in this right now, you can just reply to that email for the webinar itself and just ask. If you want something a little bit lower commitment, you can also join us for an event. You can follow our blog, you can attend an upcoming webinar, you can watch previous webinars, and you can attend the virtual open forum workshop, which is coming up in June, which I strongly encourage. Okay, with that, I am finished, and we are more than welcome to take a few questions.